So good morning, good afternoon, good evening. So I'm going to be taking you through numerical linear algebra. I'm going to be taking you through numerical linear algebra. This involves solving basically linear systems. Yeah, we're going to be solving linear systems of the form, let's say something like this, where this A is a matrix. Let's say that yeah, basically A will be a square matrix if you're to solve such a linear system, and this B is a vector n, and also x is a vector. Can denote my vector in that way, something like that. So our linear system will always have a notation. So here we are going to be solving linear systems. We are going to be solving linear systems of the form, just like I've said, of the form x equals to b. So the basic notation, one of the notations that we can use, the notation of the linear systems, like how the linear systems can be written, is like, let's say a1 x1 plus a12 x2 plus, and this goes to a1n xn, which is equal to, let's say, bn. So someone else can have, so this can be a2 1 x1, this will be a22 x2 plus, it's also plus, so this can be like a, yes, 2, this is n, this is still xn, this can be b1, then this is b2. However, we can do this for several values basing on the size of A, of matrix A. So this goes up to, let's say, an1 x1 plus an2 x2 plus, let's say, this is an xn equals to bn. So something like this, just like I've said, like we are solving linear systems, and from this kind of system, and from this expression, we can generate this x equals to b, where our A is now the matrix which has this a11 up to a1n, and this goes up to an1 up to ann, something like this. So our matrix is that, our A, then our matrix X, this is a vector, so this is like x1 up to xn, and our B can be written in that way, is going to be b1 up to bn, something like that. Therefore, you find that for you to be in the form ax equals to b, so I can combine this here, this is our A, so I have my A there, then I have my x is an unknown, so we don't know it, so it's the one we are looking for, but but this entire expression is equal to b. This entire expression is equal to b, something like that. So therefore, so this is the general form of how the linear systems. So in most cases we shall be given this, and we shall be trying to generate the matrix A, the X and B. You have to be careful because sometimes they can interchange, in case you have been given an example. So you need to be careful. So some of the observations that we see, some of the observation is that in this case we focus on square matrices. We focus on square matrices when we are solving for these linear systems. However, there are several methods of solving this kind of systems. However, I'm basically interested in the iterative methods of solving these linear systems. So some of the theorems involved in this. So we have like the theorem for solving linear system. Okay, our first theorem that we are going to consider when dealing with solving linear systems is, so suppose we are given a matrix A which is in Rn by n, an n by n matrix. Then we have matrix A which is equal to that xb which is in Rn, and this has a solution and it's unique. So we have this kind of system has a solution and it's unique. The solution is unique if and only if x in Rn, if and only x is in Rn such that my ax equals to b. So in this case we state that this A is invertible. A is invertible. We state that the rank of A must be equal to n for rank. We also state that my x equals to 0 has only the trivial solution, this equals to 0. And the other thing that we consider is that the determinant of A is not equal to 0. So the first theorem that we consider is that given A, which is in an R square matrix, given A, which is a square matrix A by n, this we have our linear systems, we have x and b which are vectors. This system has a solution and it's unique if these are satisfied. One of them is that A is invertible. What do we mean by A is being invertible? It means that there exists a matrix B which is also square such that A times B is equal to B times A, and they both give you the identity matrix in n, which is also an n by n matrix. So the rank of A should also be equal to n, so it should be full rank. Then we see that our Ax equals to 0 has only the trivial solution, x equals to this here, like whenever we solve this and it's equal to 0, it should only have the trivial solution, x equals to 0. The moment that is not the only solution that you have, then it implies that you can't find the unique solution to this problem. You can't find the unique solution to this. So then we also see that our determinant of a is not equal to 0. The moment the determinant of a is equal to 0, we won't have a unique solution, but we shall have multiple solutions for x. So the only way we can write a unique solution is if this is equal to 0. So we can prove some of these ones. For example, we can prove some of these assumptions. For example, we can prove Roman numeral 4. Roman numeral 4 can happen if and only if the second one happens, or vice versa. So it's like they are saying that if the determinant of a is not equal to 0, okay, like the determinant of a is equal to 0 if and only if Roman numeral 2 holds, if and only if the rank of a is equal to n. So how do we prove this? So we prove this so I can be like, so what do I do? That's what I want to show. So I can suppose, so if I suppose that the determinant of a is equal to 0, the moment the determinant of a is equal to 0, we should all be aware that for matrices, let's say this matrix, this is just an example. You see this matrix, its rank is not equal to n itself. The rank of this matrix, let's say this is A. The rank of this matrix A is a 1. Because the rank is basically the number of linearly independent rows or linearly independent columns. But in this case, the linearly independent row is only 1, so it's the one we take. So the rank is 1. So the moment the rank is 1, the determinant of this is equal to 0. In this case, the determinant of A is equal to 0. When you take row by column, that row and that column. So if I suppose that the determinant is a 0, it implies that our rank will be less than 2, the size of this matrix. So meaning, now if I suppose that the determinant is equal to 0, the moment the determinant is equal to 0, this only happens if and only if the rank of A is less than, the rank of A is less than n. And when you try to look at this, this is the negation for and that is the negation for the determinant of A not being equal to 0 if and only if the rank of A is equal to n. Don't be tempted to say that the rank of A is greater than n, because that is impossible. The only two cases we have is either the rank is equal to n or the rank is less than n. So something like that. So as simple as that. So if you can state this and state that it is the negation for this, then it implies that this holds. So I will stop there for my proof. So then we can also show another one. We can also be like, you see Roman numeral 3, 1 implies, now this time I'm saying implies, I'm not saying if and only if, implies Roman numeral 3. So what does this mean? Roman numeral 1 implies Roman numeral 3. What does Roman numeral 1 say? It says that, so now it means they are supposing, or they can say if A is invertible, if A is invertible, then Roman numeral 3 comes in. Then AX equals to 0 has only the trivial solution. This one has only the trivial. If A is invertible, then that has only the trivial solution. In my case, whenever I'm proving, so this is an if situation. So meaning they are supposing that A is invertible. Suppose that A is invertible. So if A is invertible, what does it mean to you? It implies that there exists. So this implies that there exists a matrix B. So I'm supposing A is invertible. However, earlier on we stated that this is an Rn by n matrix. So meaning there exists B, which is also an Rn by n matrix, such that so this is such that IAB equals to BA equals to I. Something like that. So therefore, what does this mean? Yeah, that's when it is invertible. Now I want to show this. So you begin with what you know. So the statement I've begun with is what I know in this case. So I know this. The moment that is implied, this is what I expect. So now I want to show that it has only, then this has only the trivial solution. So now from the AX equals to 0, we have seen that the inverse of A exists, meaning I can take the inverse on both sides, A inverse AX to be equal to A inverse 0 irrespective matrix multiplication. I've taken it on the left hand side, so even this side it's on the left hand side, however it is multiplied with 0. So therefore here I just get the matrix X equals to 0. Therefore, hence this is proven that our AX equals to 0 has strictly has exactly one trivial solution. So this has exactly one trivial solution, and that solution is X equals to 0. This is a vector. It's okay if you write it like that. It's a vector. X is in Rn. So it's okay if you can write it like that. So what does Roman numeral 2 say? So my Roman numeral, I can also prove this. I can also prove that Roman numeral 3, if this, then Roman numeral 2 holds. So in this case we suppose that like they are okay, what they are claiming is that if ax equals to 0 has a trivial solution, has only the trivial solution, x equals to 0, then this is what they are claiming. Then the rank of A equals to n. So how do we prove this? So how do we prove this? Now we show, first of all, we, just like I said, so you begin from what you know. Already. So you suppose that our ax equals to 0. Now if our ax equals to 0, what does this mean? What does this mean? It means that has only that solution, so it's okay for me to okay, let me use an example. Using an example. So if I'm using an example, let's say our A is a 3 by 3 matrix, A11, A12, A13, A21, A22, A23, A31, A32, A33. So meaning this ax is now going to be A11. It's going to be my matrix here. This one. So this is going to be my matrix. This times x. Now this is going to be in R3, x2, x3, and this is equal to 0. Yeah, but this is also the 0 matrix. So this is 0, 0, like that. So that is 0, 0. So let us suppose that. So you find that I can write each of these ones like this in column form. So it's okay, I can write that in column form, and it's like, if I'm to write this in column form, this is like, let me say A1, that to represent that column, A2 to represent that column, A3 to represent that column, and this is multiplying with x1, x2, x3 equals to 0. Okay, here these ones are 3 by 3, so this is 0, something like that. So we have that, therefore this is A1, that x1 plus A2, x2, when I look at like it's a linear combination. So this is A3, x3, but this is a vector, and this, they're supposed to give you the 0 vector. So what do we see? We see that this, but so we see that if so we know that given that these x1s, these column vectors, these ones A2, A3 are strictly linearly independent. Meaning that none of them can be expressed in terms of the other two. So if they are linearly independent, then the only way we can have such a situation, if they are linearly independent, then the only way we can have something like that is if is if the x1s are equal to x2 are equal to x3 and the other ones which are equal to 0. So this shows you that the span, therefore this shows that the span of each of the three vectors, a1 that, a2 that, a3, so the span of these vectors, they span R3. Since they are linearly independent, meaning they can be used to span R3. In any vector in R3, this means that any vector in R3 can be written as a linear combination of these. So they can span R3. Therefore, this implies that the rank of the matrix A from which these ones come from is equal to the rank is equal to 3. I can say that. So through this example, I think you can use it to show that whenever I have any matrix that has only 0 as the trivial solution, it implies that, remember, the matrix has only 0 as the trivial solution. So when you multiply these and you have a 0, this is only equal to the 0 matrix. Because it's our only trivial solution for this. That's why here we are claiming that these ones are linearly independent and this holds. This has been given by the fact that this has only the trivial solution. So this x1, x2, x3, they must be zeros. That's why if they are zeros, then this must be linearly independent to one another. Therefore, they span R3 and their rank is 3. So this is sufficient enough for you to conclude that whenever this has a trivial solution, hence proved. So whenever we have a trivial solution, whenever this ax equals to 0 has a trivial solution, then it's okay for you to conclude that this rank of A is equal to n, where A is in R, n, something like that. So we proceed. So Roman numeral, we can also try to show this. We can also try to show that Roman numeral 2 implies Roman numeral 1. We can also try to show that Roman numeral 2 implies Roman numeral 1. So, what does Roman numeral 2 say? So, Roman numeral 2 claims that so if this is what it represented, that if the rank of A equals to n, then A is invertible. Then A is invertible. If the rank of A equals to n, then A is invertible. So we want to show that. So what do we do? So we'll prove. So how do we prove this? So just like I've already said, you suppose that the rank of A equals to n. So you suppose that the rank of A equals to n. So we want to show that A is invertible. You can write it, you can keep it in mind, it's okay. You want to show that A is invertible. But we know that I have already stated that A is invertible if there exists a B such that A and B equals to B and A, and this will give me the identity matrix. But since now I begin with what I know, this is what I want to show. So since the rank is that, then meaning that from my problem AX equals to B, and we know that A has full rank. A has full rank. So this A has full rank because the rank of A equals to N. Because the rank of A equals to N. That's why I'm claiming that A has full rank. So meaning that actually from the previous thing, so this implies that the span of each of the columns from, let's say, 1 up to n, of each of the columns in A must give you the span, like the span Rn, just like we have just done. So this implies that so this means that for any B, for all vectors B in Rn, this means that for all vectors B in Rn, they can be written as a linear combination. For all vectors in Rn, there exists x this, xj, which are columns, which are in A, columns in Rn. I can't say like they're in A, they're just columns in that, such that there are some alphas, let's say alpha 1, x1 up to alpha n, xn, which will give you B, which will give you that vector B. So now, but for us now, I'm doing all this but because our interest is in, because I want to show that it is invertible, my interest is in forming a matrix B. My interest is in forming a matrix B which will satisfy this. But we have just seen that our AB equals to I. This is what I'm interested in. So basing on this, I've just constructed a column which can be in B. This column can be in B, so we can construct construct matrix B such that AB equals to BA equals to I. Something like that. Where the columns in B, where the columns in B, okay, I can write this. B, if AB is going to be equal to I, so these are the columns in A. I can go up to AN. Those are columns in A. They're going to multiply with matrix B. These are columns in B up to BN. However, these columns can be made. We can be made because we know that the rank of A equals to N, and that rank of A can span matrix vectors in Rn. So since we can span vectors in Rn using the elements of A, I think it's better if I write A here. So this is A1. So using the elements in A, I can span R this, and this B, matrix B, is made up of these these columns. So they can be spanned using vectors in A. They can be written, these vectors in B can be written as a linear combination of these. since the rank of this is equal to n. So therefore this implies that this is equal to this is equal to I. So we span these vectors in B using the vectors in A in such a way that the vector B that we are going to form takes us to I. We can just construct it. So now we can complete using, so by a column, we can multiply a column by column multiplication, or using our row by column, it's okay. So using our column by column multiplication, so if I'm multiplying column by column multiplication, I get a column in B. Then it multiplies all. I get like a column in B, then it multiplies all the columns in A. However, the column in B, so let me try to simplify this. However, the column in B, let's say B1, it's going to be like, it's a column, so it's made up of, let's say B in the I1. Remember, the column comes last. It's the column that remains the same up to B M, but this is still a 1. So this column here multiplies all the matrices here, and that will give us just a single element within I. So this is what I mean. So this will be B11 will multiply with that, plus B21 will multiply with it to that. So I will continue in that way up to Bn1 multiplying with An this, and this will just give us a single column in I. It will give us that column in I. I can call it EJ. Can call it EJ, and this EJ is equal to 0 up to some, because this is up to some that actually, if I multiply by B1 and it's multiplying by this, meaning this is supposed to be E1. Yeah, this is now 1, 0, 0 n times. So that's what we are supposed to get. So we can also multiply like with a jth column here. Using a jth column, can use a jth column in B. When you use a jth column, this is like B1. Now this is A1. These ones remain the same. This is B21. No. This is B1J. This is B2J. These ones remain the same, plus, so I come up to BNJ since I'm in the jth column. So this will give us the AJ to give us that jth column in I, and it is made up of zeros elsewhere up to 1, and this one is in the this now continues up to 0, and this is the jth column. This is like the jth term. That's where the 1 is. So you find that all the columns all the ej columns in I can be attained. All the ej columns can be attained for all the ej columns can be attained, and therefore AB will end up being equal to the identity matrix. Even when you try out for BA equals to I, it will still hold. So our argument is, as far as this proof is concerned, you suppose the rank is this. If the rank is this, if the rank is equal to n, then it implies that this matrix A has full rank, and therefore it can span its columns. The columns of matrix A can span the Rn, meaning that when I want to multiply A times B to give me I can construct the matrix B myself by writing each of the columns in B as a linear combination of the matrices in A, of the columns in A. So that's how I got this B. And when you use column by column multiplication of this and this, you find that through column by column multiplication, I can get each of the columns in the identity matrix, this. So I have my jth column in B, can be written in that way. Therefore, the columns can be attained. In I can be attained. Therefore, my AB equals to I and my BA equals to I. Something like that. Okay, so we have tried to prove so there we just build the matrix ourselves. Then the other one, we can also try to show I think this will be the last, and it's the easiest. Can also prove that if A is invertible, then AX equals to B has a unique solution. AX equals to B has a unique solution. So this is one of the easiest, but because we know, because basing on what we have done, this is now a piece of cake. So we see that A is invertible. If A is invertible, then AX equals to B has a unique solution. So we know that if A is invertible, you just suppose, like, you begin from what you know. So suppose A is invertible. So this implies that there exists a B which is also in Rn. It's in the same space as A, such that AB equals to BA equals to I. So meaning that my AB, for my AX equals to B, I can take its inverse of this, of AX, equals to A inverse of B. Therefore my X equals to A inverse of B, something like that. So this is the unique solution they were talking about. So if this is invertible, if this is invertible, since A is invertible, I can come to this step. Since A is invertible, so we can still come to that step. So this is enough for you to complete. Therefore, this is the unique solution. So there exists a unique X in that is equal to that. And that is our unique solution that they were talking about. You can also try about some examples. Yeah, I think we can stop there for today. Next time we shall be talking about solutions of triangular systems. Yeah, thank you for watching. Please subscribe to our channel. More videos are coming. Thank you. Have a good night. Buonanotte. Musole bulungi. Thank you for studying with me. Thank you very much.